Hello everybody and welcome to this GCSE Chemistry walkthrough video about the using resources topic. And what we're going to look at today is a series of GCSE exam questions about water treatment, sustainable sources of copper, and we'll finish by looking at a life cycle assessments question. And as ever with these walkthroughs, what I will do is I will model my thoughts and I'll write those down in blue, and then the answers that are actually going to get you the marks, those will appear in green. So what I suggest you do is pause the exam questions when they first appear so you can have a go at them yourselves, and then listen and watch as I go through the questions to show you where to get all the answers. This first question is about the dissolved solids in a sample of water. We've got a small sample of water, only 5 cubic centimetres, and what's happening is the water sample is in a watch glass that is above a beaker of boiling water. That allows the water to be heated less fiercely, and that means we're going to be minimising any spitting because we want the water to evaporate. We don't want any of the solids to be carried out with some water that was popping in a bubble or something like that. Then we've got a table full of data, and we can see the 3 different types of water that they're investigating. Very common type of question this: seawater, river water and rainwater. Now obviously we should know that seawater will have salt dissolved in it, and river water might have more solids that have been suspended in it perhaps. And then we can see that we've got some data. We've got the mass of the watch glass at the beginning, and then we've got the watch glass and the dissolved solids at the end. So you can see that these are always larger values. And then we've got the dissolved solids in 5 cm cubed of water. What they've done is they've taken the 9.48 that you can see here, and they've subtracted the 9.34 away from that, and that's left us with 0.14 grams of dissolved solids in the sample of water that was on the watch glass at the top. And then they've done the same for the other 2 substances, river water and rainwater, and you can see that the watch glass for rainwater was 8.93, and then it was still 8.93 after the water had evaporated and the dissolved solids had been left behind. And what that means is there weren't any dissolved solids in this particular sample. And then you can see the final substance, the final column in the table, we have had some scaling up. We've had 5 cm cubed of water and the dissolved solids that are in that. This time we've got a far greater volume. We've got 1,000 cm cubed of water in this second column. And so 1,000 cm cubed is 200 times greater volume than 5 cm cubed. And so these numbers are in fact 200 times greater because you've got 200 times the volume of water. And that's where we enter the first question, because we've been asked to calculate X, which from the table is this missing value that they haven't calculated. So we know that there are 0.08 grams of dissolved solid in 5 cm cubed, so we need to multiply that by 200, or really multiply it by 1,000 and divide it by 5, which of course is multiply it by 100, 200, and that will then give us our final answer of 16.0 grams, which is all we need to do to get our 1 mark. And then the second question says 5 cm cubed is quite a small volume of water. I've already said that, but why is it a small volume? Well, a small volume is going to any mistakes are going to have a bigger impact on your final answer if you've only got a small volume of water in the first place. If you get this, the spitting that I mentioned earlier, or if errors creep in somehow, a small volume is going to be really vulnerable to those kinds of mistakes. And so therefore, what you're being asked here is, why is a larger volume more advantageous? All you need to say is quite simply, it is more accurate to use a larger volume. Any errors won't have so much of an effect. But of course, what will happen as a result is it will require more time to get all the water to evaporate, because there's more water to evaporate, or similarly, more energy needed to evaporate all of that water. I would like you to focus on comparative language here. Make sure you are saying more for both of these, because we are comparing a large volume to a small volume. And then finally, we are being asked to move on to think about potable water and pure water, and you're being asked for the difference between potable water and pure water. And so pure water is only water, and potable water is water that is safe to drink. And so what we're being asked now is to compare water that's safe to drink with something that is literally only water. And so our answer just needs to say, well, potable water might have dissolved solids in it, which are perfectly safe to drink, and it might also have chlorine in it that was used to make the water safe to drink in the first place, whereas the pure water won't have any of those things. Or you could say it is only water. This next question is going on to look at how these two samples of water, groundwater and seawater, are treated to make them potable, make them safe to drink. Now, before we start looking at the actual answers, let's first of all look at the fact that this is only 3 marks. And so we're also being asked to describe. And so what that means is we are not going deep into this question. We are just listing the actual steps that are taking place. So what I'll also do is I'll say why we do the steps, which we would need to do if this was an explain question. So I'll go to blue for that one. So first of all then, let's focus on groundwater, and the first thing that we have to do for groundwater is we have to filter it. So groundwater is filtered, and that is done to remove any dissolved solids that might be in the water. And so that might be any, twigs, gravel, or anything that is insoluble. Sorry, I said dissolved solids. I mean insoluble solids. And then the second thing that that needs to be done for the groundwater is it needs to be sterilised, and that is using chlorine. So let's put that in there. We probably don't need that for the second mark, but it's good to know that anyway. But it's sterilised using chlorine, and what that does is that kills pathogens. But again, like I say, you won't need that for a describe question with so much else going on. And so that's groundwater. It's filtered and it's sterilised. The seawater, though, needs to be distilled because there is salt dissolved in it. So seawater has this additional step because we need to remove the sodium chloride or separate the water from the sodium chloride. So distillation needs to happen for the seawater, or alternatively, you could use reverse osmosis, and that gets the salt out. But you wouldn't say that, you would need to be far more technical than that. The name for the removing of the salt probably would also get you a mark here. We'll put that as a third option, but desalination needs to happen to make sure all of the salt is removed. And then the question goes on to consider another sample of water. We've got 6.50 grams of this water, and we're told that the percentage of dissolved solids in there is 2.2%, and we've been asked to calculate what the actual mass of dissolved solids is. And so what we're effectively being asked to do is work out what 2.2% of 6.50 grams is. And to do that, what we have to do is we have to express that percentage as a fraction by doing 2.2 divided by 100. That's 2.2% written as a fraction. And then we need to multiply that by the total mass of solid that we've got, which is 6.50 grams. And so we are now finding out we've got 0.143 grams of dissolved solids in this 6.50 grams sample of water. We're going to look at another water question now. This time we're looking at the processing of sewage, or in other words, wastewater. And so what we've got here is a diagram showing how sewage from homes passes through 4 separate tanks, which they've labelled on the side here, A, B, C and D. And you can see that they're asking us about A and C and D, but they're not asking us about tank B, which I will mention very briefly. So name the processors happening in tank A. And so we just need to dive straight in with the first one. This is called screening. And what happens here, so we've been asked to name it, by the way, so we don't need to go into any greater depth than that. But you can see we've got a metal grid on the side. And what that does is that removes solids. And that's called screening, removing of solids using that metal grid. And so that's things like twigs, cotton buds, wet wipes, and all that kind of toiletries that people have disposed of, perhaps in the wrong way rather than putting it in the rubbish. And then the second thing that's happening, and you can see that on the diagram as well, that's these dots at the bottom of the tank. That is sedimentation. And that's where they let the water stand for a while, and things like grit will sink to the bottom of the tank and therefore be removed from the water itself. Then the question skips tank B, but I just want to mention briefly what happens here is we've got two substances which separate out, and we've got the effluent, which is pretty much water, but what's in the water is organic waste materials that are kind of so small particles they stay suspended in the water. And then we've got the sludge, which has got more organic waste, more sort of solid organic waste, which sinks to the bottom, and that then gets treated with bacteria, and they respire anaerobically, and that then makes the sludge suitable for things like fertilizers, whereas the effluent is treated, as you can see in tank C, we're moving on to the actual next question, with the air bubbles. And so the air bubbles are providing oxygen to the tank, and microorganisms in that tank use that oxygen for aerobic respiration. And during that process, the waste is broken down, it's digested. And that's all that you need to say, even though we're getting 4 marks, we're not using half the lines there, really. And then we move on to the final tank, tank D, and what you can see is that more sludge settles at the bottom of this tank as well, and we've got the effluent, the watery part of the wastewater, floating on top of that, or just being on top of that. And last of all, what happens is it is sterilised, and so this is exactly the same as the previous question, except we are, in fact, now being asked why it is sterilised, and all we need to say is to kill bacteria or to kill microorganisms or microbes or pathogens is probably my favourite of these options, actually. Kill pathogens. This first part of the question is actually a bit of repetition from the previous question, which was from a different year, by the way. You wouldn't get both on the same paper. And they're talking about desalination. This time, though, you'll notice that they're saying desalination by distillation. And so you're being asked to name one other method of desalination, which does mean that you need to learn both distillation and reverse osmosis, which is the answer. On this occasion, you can't just rely on knowing distillation, because here they've said give one other method. And now we've got another bit of repetition, because what you're being asked to do here is to describe a method that could be used to find the concentration of dissolved solids in a sample of seawater. So this is the alternative form of the question that we've just been looking at, where you were given some data about this experiment. Here you're being asked to plan it or explain how you would do it. Again, you've been given tons of lines. You don't need to use all of the lines to get the 6 marks. So what we know, because we've just seen the diagram on the previous page, we would need to weigh an evaporating basin or an evaporating dish. Either word is absolutely fine. And then that would be when it's empty. And then after you've done that, you need to add a known volume of water, because you can't just say add water to it. We need to know how much the volume we have used. And I do prefer volume rather than amount, by the way. When you're working with liquids or gases, in fact, use the word volume. And then, as we know, what we have to do next is we heat the dish, and that evaporates the water. You don't need to go into the detail about heating it on top of a beaker or anything like that. We just need to say heat to evaporate the water. And then what you would have to do is you would reweigh your dish. And so what you would do is you would subtract the mass before, the empty basin, from the mass that we've got now, which is the basin plus the solid. And what we're doing there is we're calculating the difference in mass before and after. That's probably the easiest words to say. And then what we would have to do is that's 5 marks. And then what we'd have to do is we would have to kind of finesse this with one extra little bit of structure to it. So we could either divide the mass that we've found by the volume of water that we started with, and that would allow us to find our concentration in grams per cubic centimetre, for instance. That would get us our 6th mark. Or we could talk about actually repeating our method or carrying on heating a bit further until the mass remains constant. That's called heating to a constant mass. And what that does is that allows us to be confident that we have removed all of the water that was in our original sample, and we haven't got sort of slightly damp solids in the bottom of our basin. This next question is about the production of copper. In particular, what it's about is the sustainable production of copper. And what we're told in the question is that in the year 2014, so that was a few years ago now, 22 million tonnes of copper were demanded. So that's how much we needed to meet our needs. And the world reserves of copper are 700 million tonnes. And so we can do some simple maths here by taking 700 and dividing it by 22, and we find that the answer is about 35 years of copper in reserve. And so we can use that in our question in a moment, in our answer. And then we are told that copper today is obtained from ores, and ores are mined. And in the mine, the ore is heated in a furnace to produce copper sulfide, and then copper sulfide is reacted with air, and that produces copper and sulfur dioxide. So overall, we've gone from ore to copper sulfide, and from the copper sulfide, we've gone to copper by itself, but we have got sulfur dioxide as a byproduct. And then last of all, we are entering into the kind of the main thrust of the question. We're told that phytomining is an alternative way of getting copper out of low-grade ores. And so low-grade ores are ores that it wouldn't be worth having a mine for. You wouldn't dig a mine to get low-grade ores. It means you wouldn't get much copper out at the end of it, and so all your costs wouldn't be worth the amount of copper that you got at the end. You wouldn't get your money back. And so what phytomining does is it uses plants as an alternative, and the plants absorb the copper compounds, and these are then burned, and copper is extracted from the ashes. So here's what the process looks like overall along the bottom. So you can see that what we've got is we've got the plant, which is obviously in the ground, and we've got the roots that are below the ground, and we've got the copper, but not very much of it in the soil. And so what will happen is that copper will enter the plants through the roots, through a process of active transport, and then what happens is we burn the plants, and the plants then leave behind the copper in the ash, and that's a way of getting lots of copper without having to dig a mine. So the question then gives us a statement which says more copper should be extracted by phytomining, and then we're told to use the information to justify the scientist's statement. So we are agreeing with the scientist, and we're being asked to say why we agree, but we've been given tons of help along the way in the question, loads of data. We don't have to remember lots of facts for ourselves. So first up, let's return to all the notes that we've been making while we've been reading the question. And let's say first and foremost that phytomining conserves supplies of ores. That's what they told us in the question. If we're using phytomining, we aren't using other ores. And that's really important because copper won't be available for long at the present rate of use. We have only got about 35 years left of our copper reserves. And then we need to kind of probably tackle two main issues. And we don't need to say everything that I'm about to write, by the way. We'll explore what the mark scheme would actually require in just a moment, but I'm just going to keep making some bullet points. So phytomining will conserve supplies of fossil fuels because the process itself doesn't use very much energy. And so as a result of that, we will need less fuel. And so that means that will lower the costs because we aren't using as much fuel. Not only that, we aren't burning fossil fuels, so that means that we won't be producing as much carbon dioxide or greenhouse gases generally. And that means that we aren't contributing to global warming or climate change in the same way that copper mining in the traditional way does. And then last of all, they did mention sulfur dioxide as being produced, and we know that from a previous topic in the atmosphere that sulfur dioxide can cause acid rain. So phytomining doesn't contribute towards acid rain in the same way. And then if we just focus on the mines and the negative aspect of mining, well, mining scars the landscape and it produces noise pollution, the act of mining itself. And it also has the problem that it destroys wildlife habitats too. Now, phytomining, obviously we're burning plants, but we aren't needing to mine ores if we're doing phytomining. And so what we can categorically say is that we aren't scarring the landscape in the same way, and we aren't destroying animal habitats as well. So huge advantages of phytomining. So we've made lots of bullet points here. We wouldn't need to say them all. The mark schemes for this are sort of usually like a best fit scenario, and to get to level 3, which is what I'm teaching you to get to, that would get you 5 or 6 marks. And the difference between that is that you would need to make sure that you've written a detailed and coherent and logical justification of the scientist's statement with plenty of links between the statements that you're making, which is why I'm sort of grouping them in the way that I've done here with my little kind of brackets to say that these are connected ideas. And we need to make sure that we are both saying good things about phytomining and making sure that we're being comparative and saying that the mining as an alternative method of production would do the opposite. And so we can probably get some sort of 2-for-1 sentences in here, because you don't have to have used the exact words that I've said. And we can say, for instance, mining scars the landscape, whereas phytomining doesn't, and other sentences like that. So overall, I would aim to hit something from each of my bracketed sections, but I wouldn't expect you to have made every single point that I've bulleted inside them here. So perhaps 6 bullet points, but just making sure you're covering something from each of these sections, maybe 2 bullet points from these bigger sections. The final question we're going to take a look at starts by introducing the focus, which is about carrier bags made from polythene. So we've got a question on the first page here, which is comparing the structures, and then on the next page we'll look at a life cycle assessment question. So we are discussing high density polythene and low density polythene. We've been given 2 diagrams, and we've been asked to describe the differences in the structure and the arrangement of the polymer chains, and we're getting 2 marks for doing this. So if we just look at these polymer chains, you can see that in high density we have just got sort of wiggly lines that look like this, and then in the low density we've got these funny little branches sticking out at the side. And so for our first mark, that's what we need to do. So we can say both things, or we can just make one statement about one of the types of polymers. And so in terms of what we need to write, we need to say high density polythene, and we can abbreviate it like they have, has no side chains. And so as a result of that, the chains pack closer together in high density than low density polythene. It's important to get a comparative sentence in there for our second mark. You could obviously have come at this from the other angle and said that low density polythene has got the side chains and therefore can't pack together so closely. You could come at it from that complete opposite angle. The important thing is that you are covering these 2 key points, focusing on the comment about the structure and the effect that has on their arrangement. And then the question moves on to the life cycle assessment, where we're focusing on the use of high density polythene for disposable bags, but also bags for life. And then we've got some information about bags for life can be returned to the supermarket when they're no longer usable, and then they'll be replaced free of charge, but that's not really very helpful for this question. And then we've got our table full of data, which we'll return to in just a moment, and our command is to evaluate the use of each type of carrier bag using the data and any of our own knowledge to support this answer. So my suggestion here, first of all, actually, when you're asked to evaluate, you need to make a conclusion. If you don't make a conclusion, you can't access the level 3, the 5 or 6 out of 6 marks that are available, and you're limited to maximum of 4. So we must remember to make a conclusion. Sometimes they don't mind which of the options you choose, you just need to be able to support your answer. I think here there is actually a clear winner for me, and we'll get to that in just a moment, but make a conclusion. And my advice would actually be to start with the conclusion, because then you don't get tempted to make a load of comments about the facts, then make your conclusion and kind of feel like you have to support it again by repeating yourself. So make the conclusion at the beginning and then follow it with the supporting evidence. My suggestion when you're approaching a question like this is to actually take each of the kind of facts in turn and assess the significance of the facts about our 2 options as we work down. So, for instance, the type of polymer, high density polythene and low density polythene. That's not really clear what the relevance of that information is to our answer. It's relevant, but not really to our answer. And then we've got the raw material that each of these bags are made from. Now, they're both made from crude oil, so that means that we don't really mind here. It doesn't really make that much of a difference. And similarly, if we just scoot down to the bottom, we can see that the methods for disposal are the same for both methods. Landfill, incineration, recycling are our 3 options, whichever bag we choose, which means that our final kind of decision in our evaluation has to be based on these 3 middle rows. So the mass of waste per bag, that's really significant that it is per bag, 0.42 grams for the disposable bag and 0.17 for the bag for life. So the bag for life is winning because there is less waste. And I really do suggest that you annotate it with smiley faces because that does make your decision easier. Now the mass of carbon dioxide emitted per bag in grams, well 1.6 grams is for the disposable bag and 6.9 grams for the bag for life. So the bag for life has lost that competition. And then last of all, the mean number of times we can use the bag. So disposable bag, you use it once, whereas the bag for life, you use it 6 times. So what we could do then is we can just take a look at this and say, well, the bag for life has got 2 smiley faces, and it's got 1 sad face, and it's got 2 which are complete draws. So at that depth of answer, we look like we've got a winner. The bag for life looks like it wins. But if we focus in on the fact that the bag for life can be used 6 times and the disposable bag, well, if we used 6 disposable bags, obviously 6 disposable bags would be able to be used 6 times. But if we did that, each of those 6 disposable bags would produce 1.6 grams of carbon dioxide, and 1.6 times by 6 is actually 9.6 grams of carbon dioxide emitted, which is greater than the 6.9 grams that the bag for life produces. So that smiley face hides the fact that we have to use 6 bags, which actually turns that into a sad face, I think, on this occasion. And then if we do the same thing for the waste produced in grams, waste material, not just carbon dioxide, then 0.42 multiplied by 6 is actually 2.52 grams of waste material. And so now, in terms of our answer, we need to make sure that we are making strongly linked comments that are supported by a sufficient range of evidence with correct reasoning given. So we don't need to say, again, everything that I'm about to write down, but we need to have a consistent approach and say something from each of my sections. So we need to make sure we comment on the similarities between the disposable bag and the bag for life. And as we've already said, they're both made from crude oil. That's bad because crude oil is a finite resource. That's what I mean by giving reasons why that's relevant. Now, both of them will involve production and transport, and both production and transport cause emissions of carbon dioxide. And that's bad because carbon dioxide contributes to global warming. And they can both be disposed of in similar ways, which means any negative impacts of using a landfill, well, that's relevant to both of them. And then the next section that we need to consider is the disadvantages of one type of bag or another. So let's focus on the disadvantages of the disposable bags. And so each disposable bag generates more waste than a bag for life does. Now, you wouldn't necessarily say this as well, but we could really show off here and we could say that it's about 2.5 times more waste being produced, or similar kind of greater depth using the actual data, we could say that this is 2.35 grams more waste, because that's the difference between 2.52 and 0.17 grams when you're using 6 bags. And we could also say that using 6 disposable bags causes more CO2 to be emitted. And again, we could really show off by using the data and say, well, that's actually 2.7 grams more, because 9.6 take away 6.9 is 2.7. So that's fully addressing the disadvantages of disposable bags. Now, supposing you wanted to argue that disposable bags were advantageous, it was a good thing to use disposable bags, say, well, we could say that they cause less CO2 to be emitted, because 1.6 is less than 6.9. And in fact, we could show off there again by using the data and say that this is 5.3 grams less CO2 per bag. And we can also say, though, that disposable bags, if we use them more than once, then definitely less CO2 will be emitted. Alternatively, the bag for life can be used 6 times. Well, maybe it won't be. What if somebody uses it fewer than 5 times? Well, that will definitely result in more CO2 being emitted. And also, we could just finish with an advantage being that, well, disposable bags extend less because they're made from high-density polythene. That could be a way that we make the type of polymer relevant to our answer for this question. And so to finish off, you absolutely wouldn't need to say all of these. I mean, not least because these 3 are all different ways of saying the same thing, as are these 2 and these 2. But it's important to link your ideas. That's more important than volume of ideas. Really, 4 or 5 ideas, absolutely plenty, provided you have linked it well and explained it well, and it does follow on from the conclusion that you've made. Okay, that's the end of this video. I hope it's useful. I'll see you again next time. Goodbye.